Hello everyone, today we will learn third application of derivatives, maxima and minima. It is an important application of derivatives. Maxima and minima is nothing but the highest and lowest values of a function. See here, maxima and minima are the plurals of maximum and minimum. Okay, so here maxima, the concept of maxima and minimum is most applicable in various fields such as economics, business, engineering, etc. Like to find the maximum speed, maximum profit, minimum distance, minimum cost, etc. Don't worry, we will study that later. We will solve such a real life problems. Okay. So here we will study how to find the maximum value and minimum value of a function using derivatives. Some tests are there, first derivative test, second derivative test to find the maximum and minimum values. Okay, now let's see what are the maximum and minimum values. Say for example, f of x is equal to minus x square plus 2. Okay. I have an example function f of x is equal to minus x square plus 2. See, its graph is like, okay, now let's see all the function values. Okay, I am defining this function f of x is equal to minus x square plus 2 on minus 2 to 2. Okay, it is the domain. Okay, so here let's plot the points. Here when x is equal to minus 2, so what is f of x? F of minus 2 is nothing but, substitute x is equal to minus 2, so it will be minus 4 plus 2, that is minus 2, right? Okay, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, etc. 1, 2, 3, 4, 5. Okay, that's enough. So here, see, when x is equal to minus 2, this value of this function is minus 2, right? When x is equal to minus 2, it will be y is equal to minus 2, right? So here I have to minus 3. Okay, then when x is equal to minus 1, here see what are the values included. Okay, it is our domain minus 2 to 2, so minus 2 included. Next minus 1, I am taking only integers. Okay, so minus 1. When x is equal to minus 1, f of minus 1 is nothing but minus 1 square is 1, minus 1 plus 2, that is 1. Okay. So here when x is equal to minus 1, this value is 1. Okay. Then when x is equal to, next I will take when x is equal to 0, f of 0 is nothing but 2. Okay, f of 0 is equal to 2, so here it is the value. Okay, then when x is equal to 1, okay, these all values are included in this interval. Okay, so x is equal to 1. When x is equal to 1, so what is the function value? That is, put x is equal to 1, so minus 1 plus 2, that is 1. Okay, that is equal to f of minus 1, right? Okay, so x is equal to 1, f of 1 is 1. When x is equal to 2 square, so minus 4 plus 2 is minus 2. So it will be the point. Okay, so let's join it. See, the function will be like this. Okay, see here, it's our graph. That is graph of minus x square plus 2. Here, see, it is the peak point. Okay, that is the maximum point. So here, what is the value? Y is 2, x is 0, right? When x is 0, y is 2. So here we say this function f of x has maximum value at x is equal to 0. Okay, that is this function f of x has a maximum value at x is equal to 0. So what is the value of maximum value of the function? The maximum value of the function is nothing but 2. See, what is the largest value among these? 2, right? So here 2 is the maximum value of this function, and this function has maximum value at x is equal to 0. Okay, understood? See, here it is the concept of maximum. That is, see, maximum value, here it is the peak point. Okay, so this function has maximum value at x is equal to 0, and that maximum value is the greatest among these values of the function. Okay, so here, and the maximum value is f of 0, that is equal to 2. So here 2 is the largest value among these values, right? So it is the maximum value. So how can we define maximum value of the function? That is, let f be a function defined on an interval I, okay, then f is said to be maximum, f is said to have maximum value, okay, maximum value if there exists a point, see what is the point here? 0, okay. If there exists a point C such that C in I, okay, that defined interval, okay. So C in I such that f of C greater than or equal to f of x, here all x, okay, for all x belongs to I. Okay, see that. Compared with the example, here f of C is greater than or equal to f of x. See here, this 2 is greater than all other values of the function, right? So yeah, then we say this C is the maximum point, that is maximum value of the function. Okay, that is, here this function has a maximum value at x is equal to C. Okay, and maximum value is nothing but f of C. Okay, so here this function has a maximum value at x is equal to 0 and the maximum value is 2. Okay. Okay, next let's go through a minimum value of a function. For that, let's take an example. F of x is equal to x square. Okay, f of x is equal to x square. Let's take the same interval minus 2 to 2. Okay. So here, let's draw the graph. F of x is equal to x square. When x is equal to minus 2, f of minus 2 is equal to 4, right? Put x is equal to minus 2 square will be 4. When x is equal to minus 1, f of minus 1, that is 1. When x is equal to 0, f of 0 is equal to 0. Then when x is equal to 1, f of 1 is equal to 1. When x is equal to 2, f of 2 is equal to 4. Right? Okay, let's plot the points. Here, 1, 2, 3, 4, minus 1, minus 2, minus 3. So minus 1, minus 2, minus 3, minus 4, 1, 2, 3, 4, etc. Okay. So here, when x is equal to minus 2, f of minus 2, that is f of x or y, okay? F of minus 2, that is y is 4. Then, when x is equal to minus 1, f of minus 1 is 1. That is, when x is equal to minus 1, y is 1. When x is equal to 0, y is 0. It is the point. Okay. When x is equal to 1, y is equal to 1. Okay. When x is equal to 2, y is equal to 4. So let's join. So we have got a parabola towards y-axis. Okay. So here we observe that, see, it is the point, okay. So here the least point at x is equal to 0. At the origin, right? So x is equal to 0, y is also 0. Okay. So here there is no maximum value. Okay. That is, this function has no maximum value. Here here this function has minimum value at x is equal to 0. Okay, it is the least point. Okay, so here this function, we say this function f of x has minimum value at x is equal to 0. And what is the minimum value of the function? The minimum value of the function is 0. Okay, see, 0 is the least, that is least value among these values, right? So here this function has minimum value at x is equal to 0 and value of the minimum value of the function is 0. So how can we define minimum value of a function? Let f be a function defined on an interval I, then f is said to have minimum value in I if there exists a point C, okay, C in I such that f of C is greater than or less than, f of C is less than or equal to f of x, okay, f of C is less than or equal to f of x for all x belongs to I. So it is the definition of minimum value of the function. That is, f be a function defined on an interval I, f is said to have minimum value in I if there exists a point, here what is the point? 0, okay, C in I such that f of C is less than or equal to f of x. See, here f of C is the least value, okay, among all the values of the function. Okay, see here 0 is the least, smallest value among these values. Okay, so here it is the definition of the minimum value of the function. Here we will study two types of maxima and minima. Absolute maxima and minima, local maxima and minimum. Okay, see, absolute maxima and minimum are the values, that is maximum and minimum values of the function in its entire domain. Okay, but local maxima and minimum are the values, maximum and minimum values of the function in a specified range, that is in its locality. Okay, maximum and minimum values of the function in its locality. Okay, that is why it is called local maxima and minima. See, for example, here it is our graph. Okay, see, we can see, we observe that, see, it is the peak point, right? So here this point is the point of absolute maximum, okay, and these all points are local maximum, okay, these all points are local maximum, these all points are local minimum, this point is the absolute minimum. Okay, so here local maxima and minimum, absolute maxima and minima can be equal or unequal. So here let's study, see, local maxima and minimum, see, many points are there, see, these all points are local maximum, that is, it is the maximum value in its locality. Okay, here we will study using first derivative test, okay, how to find local maxima and local minimum values. So here, see, it is the first derivative test. Let f be a continuous function defined on an open interval I, then listen carefully. If f dash of x changes from positive to negative as x increases through c. Okay, see here, what is c? See here we have to find some functions will be given, right? Okay, so here we have to find the critical points. Okay, that is c. Okay, so we will find the critical point and say, and we will find f dash of x also. So this f dash of x changes from positive to negative when c increases, means here we will get the critical points, right? So we will take that critical point, and when x tends to c plus means right side, x tends to c minus. Okay, so if it changes, if its values changes from positive to negative, then we say c is a point of local maximum. Okay, c is a point of local maximum. Okay, so here next is, if f dash of x changes sign from negative to positive, Okay, don't be confused. If it changes from positive to negative, then the C is a point of local maxima, and f dash of x changes from sign from negative to positive, then C is a point of local minimum. If this f dash of x does not change sign from sign as x increases, okay, at C, then we say this function, that is C, is neither a point of local maximum nor a point of local minimum. Okay, now let's go through an example. Okay, now let's see how to find local maxima and local minimum of the given function. So given function is f of x is equal to minus x cube plus 12x plus 5. So first step is, what is the first step? First step is to find the derivative of f of x, that is f dash of x. F dash of x is equal to minus 3x square plus 12. Here minus 3 is common, let's take it out. So minus 3 into x square minus 4. See here x square minus 4 is in the form of a square minus b square. A square minus b square is a plus b into a minus b. So here this can be written as minus 3 into x plus 2 into x minus 2. Right? So next step is set for f dash of x is equal to 0 to find the critical points. So f dash of x is equal to 0, that implies minus 3 into x plus 2 into x minus 2 is equal to 0. That implies here x is equal to 2 and x is equal to minus 2. These are the critical points. Okay. See, next step, listen carefully. Okay, first of all, let's take x is equal to 2. See, here we will take immediate neighborhood of 2. That is left of 2 and right of, means less than 2 and greater than 2. Okay. So here immediate neighborhood of 2 the points are one and 3, right? Less than 2, we will take integers, okay? So less than 2, 1 and greater than 2, 3. So the points are 1 and 3, okay? That is immediate neighborhood of 2. Less than 2 and greater than 2. So 1 and 3. So here we have to check whether this f dash of x changes sign from positive to negative or negative to positive as this critical point increases, means that is why we are taking less than 2 and greater than 2. Okay. So here as this increases, what is the changes from the changes of sign? Okay, sign changes of f dash of x. So let's find what is f dash of 1. Okay. So first we will find f dash of 1, that is equal to, substitute x is equal to 1 here. So minus 3 into 1 plus 2 into 1 minus 2, that is equal to minus 3 into 3 minus 9 into minus 1, that is plus 9. Okay. Next we will find f dash of 3. Okay. First we should find the first is less than, that is less than 2. Okay. So that is f dash of 1. Then we will find f dash of 3. That is equal to minus 3 into 3 plus 2 is 5. Okay. Into 3 minus 2 is 1. So that is equal to minus 15. That is minus 15. See here. It is greater than 0. It is less than 0. Here f dash of x changes sign from positive to negative. Okay. At this point, as this increases, means 1 to 3. Okay. At this point. So we can say by the definition of, that is by the first derivative test, we can say here the function, that is 2 is a point of local maximum, because here f dash of x, the sign of f dash of x changes from positive to negative, right? Positive to negative as critical point increases. Okay. So here x is equal to 2 is a point of local maximum. Local maximum. Okay. Because if this f dash of x changes sign from positive to negative. Okay. Next, let's check about x is equal to minus 2. So here also we will take the immediate neighborhood points, okay, of minus 2. See here, minus 2, left of minus 2 is nothing but minus 3, right of minus 2 is nothing but minus 1. So let's take the points minus 3, minus 1, okay. So here, immediate neighborhood of minus 2, the points are minus 3, minus 1. Okay, minus 3, minus 1. So let's find f of minus 3. What is f dash of minus 3? We will find f dash of minus 3. Substitute x is equal to minus 3. So minus 3 into minus 3 plus 2 is minus 1. Okay. Into minus 1 minus 2, that is minus 3. Sorry, minus 3 minus 2 minus 5. Okay. So here minus minus minus. So totally it will be minus. So minus 15, right? Okay. So here we have got it is minus 15, that is less than 0. Next we will find f dash of, first we have found minus 3, f dash of minus 3, then we will find f dash of minus 1. That is minus 3 into x is equal to minus 1, so it will be 1, minus 1 minus 2, that is minus 3, now it is plus 9, that is greater than 0. Okay, see here. Here f dash of x, the sign of f dash of x changes from negative to positive, right? Negative to positive. Okay. Therefore, x is equal to minus 2 is a point of local minima. Okay. Because here the sign of f dash of x changes from negative to positive as the critical point increases. Okay. As the critical point increases, here f dash of x changes from negative to positive. Therefore, x is equal to minus 2. X is equal to minus 2 is a point of local minima. X is equal to 2 is a point of local maxima and x is equal to minus 2 is a point of local minima. Look at the next question. Find the local maxima and local minima of the function f of x is equal to 2x cube plus 3x square minus 12x plus 5 using the first derivative test. See here, in your question, if it is mentioned as using the first derivative test, you have to apply first derivative test itself. Otherwise, it is better to apply second derivative test because it is better than first derivative test. Okay. So, and see here, this method is consuming the time. Okay. Therefore, second derivative test is better. So, if it is mentioned, you have to apply this method itself. Okay. So, now here we will find local maxima and local minima using first derivative test. Okay. So, given function f of x is equal to 2x cube plus 3x square minus 12x plus 5. Then find f dash of x, that is equal to 6x square plus 6x minus 12. Here 6 is common. So, let's take it out. 6 into x square plus x minus 2. Okay. Now, here we have to find the critical points. So, we have to make it in the form of x plus a into x plus b. See here, multiplication is minus 2, addition is 1. So, the points are 2 and minus 1, right? So, we can write it as 6 into x plus 2 into x minus 1, right? See, plus 2 into minus 1, minus 2, plus 2 plus minus 1, that is plus 1. Okay. So, next step is set f dash of x is equal to 0 to find critical points, find the values of x. 6 into x plus 2 into x minus 1 is equal to 0, that implies x plus 2 is equal to 0 implies x is equal to minus 2, x minus 1 is equal to 0 implies x is equal to 1. Okay, so we have got critical points minus 2 and 1. So first of all, let's consider x is equal to minus 2. Here also we will take immediate neighborhood of minus 2. That is less than minus 2 and greater than minus 2. Left of minus 2, right of minus 2. That is less than minus 2, that is minus 3, right? In a number line. See, if it is minus 2, left of minus 2 is minus 3, right of minus 2 is minus 1. That is less than minus 2 is minus 3, greater than minus 2 is minus 1. Okay, so here x is equal to minus 2, we will take the points. The points are minus 3 and minus 1, right? Minus 3 and minus 1. Not minus 1 and minus 3, because here we have to prove f dash of x changes from negative to positive or positive to negative as critical point increases. Okay, so minus 3 to minus 1. Okay, that is why we are taking left of minus 2 and the right of minus 2. So that is less than minus 2 and next greater than minus 2. Okay, okay. So here minus 3 and minus 1 are the points. So first of all, let's find f dash of minus 3. F dash of minus 3. To find the sign, okay. F dash of minus 3, here it is f dash of x. Put x is equal to minus 3. 6 into minus 2 plus minus 3 plus 2 minus 1 into minus 3 minus 1 minus 4, that is minus minus become plus. So plus 24, it is greater than 0. Next we will find f dash of minus 1. Okay. First we have found f dash of minus 3. Next we will find f dash of minus 1. F dash of, put x is equal to minus 1. 6 into minus 1 plus 2 is 1 into minus 1 minus 1, that is minus 2. Okay. That is minus 12, that is less than 0. Okay. So here see, we observe that this function, that is f dash of x, sign of f dash of x changes from positive to negative, right? Positive to negative as this critical point increases. Okay. So according to the first derivative test, we say x is equal to minus 2 is a point of local maximum, because positive to negative, okay, changes the sign from positive to negative. Therefore, x is equal to minus 2 is a point of local maxima. Then next let's consider the point x is equal to 1. At x is equal to 1, so let's take the immediate neighborhood of 1, that is less than 1 and greater than 1, but left of 1, right of 1, that is in a number line. If it is 1, then left of 1 is, we are taking integers, okay. So left of 1 0 and right of 1 2. Okay. So here the points are 1 0 and 2. Okay. 0 and 2. Okay. So first let's find f dash of 0. Substitute x is equal to 0 here. So 6 into 0 plus 2 is 2 into 0 minus 1 is minus 1, that is equal to minus 12, that is less than 0. Next we will find f dash of 2. Okay, we have found f dash of 0. Next we will find f dash of 2. Substitute x is equal to 0. Sorry, x is equal to 2. 6 into 2 plus 2 is 4 into 2 minus 1 is 1, that is equal to 24. Here it is greater than 0. See here. Here the sign of f dash of x changes from negative to positive. Okay, negative to positive. Therefore, x is equal to 1 is a point of local minimum. Okay, therefore x is equal to 1 is a point of local minima. Okay, why? Because f dash of x changes from negative to positive. Okay, so according to the first derivative test, we say x is equal to 1 is a point of local minimum and x is equal to minus 2 is a point of local maximum. Now let's learn second derivative test. F be a function defined on an interval I and C belongs to I. If f double dash of C exists, then first one, x is equal to C is a point of local maxima if f dash of C is equal to 0 and f double dash of C less than 0. Okay. Remember, if f double dash of C less than 0, then C is a point of local maxima. Okay. And x is equal to C is a point of local minima if f dash of C is equal to 0 and f double dash of C greater than 0. Okay. If f double dash of C greater than 0 and f dash of C is equal to 0, then C is a point of local minima. Then third case is the test fails if f dash of C is equal to 0 and f double dash of C is equal to 0. See, in this case we use first derivative test and test whether C is a point of local maxima or local minima or a point of reflection. Okay. So after going through examples, we will understand very quickly. It is very simple. Okay. Finding the local maxima and local minima using second derivative test. Let's go through some examples.